Astronomy 220. I thought we'd start off our first lecture in the prologue by looking at a few nice pictures. This first picture shows the Earth with a beautiful sky up above, a colorful sky, and you might recognize several astronomical features here. First of all, the Earth itself is an astronomical feature. But this beautiful sky is the aurora borealis, the northern lights, and the colorful effect of that is something that we will explain later on in this course. Also, you may recognize, in particular, the Big Dipper in this aurora borealis. So obviously, this is in the northern hemisphere. And we're quite north in order to see the effect of the northern lights. Here's another interesting picture. It's a satellite imagery of the Earth itself, or of the United States, and a little bit of Canada. And we can see some of the northern lights effect here in northern Canada, and we can see the lights from the cities in the eastern United States. Particularly interesting to me is how large the lighting is from the Atlanta area, and in comparison, how small Birmingham and Huntsville, Decatur is. In fact, the Atlanta area is almost as large as the Chicago area, which is kind of surprising. Here's a look from space, about as close to entering space as you can get, looking down upon the Earth, and you can see the top cloud cover. This is only about 70 miles up from Spaceship One, the first commercial flight into space. If you go 63 miles up, you first enter into space. So that's only 63 miles up from the surface of the Earth. The Earth's diameter is 8,000 miles, so the radius of the Earth is 4,000 miles. So if you imagine that you are going 63 miles up from a diameter that's 8,000 miles, you get an idea of how thin the Earth's atmosphere actually is. The Earth is pretty large, and you just see just a very minute curvature of the Earth here. But in order to go into space, you only have to go 63 miles up. Here's a look at the Earth from space. I never tire at looking at pictures from space of our planet, and again you can see nice features on the planet. You can't see much of the atmospheric effect on here. You can see the clouds, but you can see how thin our atmosphere is. But in particular, it's kind of interesting to look at how easily Madagascar seems to be able to fit into the African continent here. Here's one of my favorite pictures. It is from the locality of the moon, looking back on our Earth. And this was taken by Apollo 8, which was the first manned spacecraft to make it to the moon, to actually go around the moon. The purpose of that mission was just to prove at that moment that we could do that, and it was not to land at that moment, just to go around the moon. So this was taken in Christmas time, 1968, and as they came around, they were taking a look at the moonscape and the Earth at the same time. A very neat picture. Here's a picture of one of the Jovian planets. In particular is Jupiter. In this image you can't see the red spot, but you can see a couple of the moons of Jupiter's, Galilean moons, one that looks white and one that looks rather bluish, and you can see the shadows of these moons on the planet, these black spots, and you can see a shadow possibly of another moon. Most likely this white moon is Europa, which is an ice-covered moon that has a deep water ocean underneath that ice. And very likely this blue colored moon is Ganymede, one of the largest moon in the solar system. Here's another Jovian planet, Saturn. Very spectacular sight. And one thing that makes Saturn so bright in the sky is its ring system. Increases its brightness by twice as much. Right now, in 2009-2010, the ring system is becoming more edged on, so Saturn won't be so bright for the next couple of years. Here's looking at the Saturn ring system, and Saturn has a number of moons that are near the ring system or even a part of the ring system. And I believe this one is Dione, but I'm not really sure. Here's a look at the Sun over the course of 11 years. The Sun goes through a cycle of activity. In particular, in the middle of this particular cycle, it is not very active, and then becomes more active towards the end of this cycle. And that activity has an effect on us, in particular our communications. When it's more active, we get more particles thrown towards us from the Sun, and that affects our communications and transmissions. It also affects our weather. So our weather is on this Sun cycle as well. This is an 11-year cycle, but the true full cycle of the Sun is 22 years because the magnetic fields of the Sun reverse direction every 11 years. So the full cycle is 22 years. Here's a nice picture showing a constellation up here. The constellation is not the Big Dipper or even the Little Dipper. It is the Seven Sisters, the Pleiades, or the Subaru emblem, which I think only shows 6 stars. And down below is a bright object, which in this picture happened to be Venus. But it was so bright that you could not see the details of Venus. It would not have been a spherical image in this case. It would have been a phase of Venus. But it's so bright that it just comes out looking like a twinkling star. Here is another beautiful image taken by the Hubble Space Telescope. This is the Cat's Eye Nebula, and it's really 2 explosions of stars, and what's left is a white dwarf, possibly double white dwarf in this one, at the center. And it was called a planetary nebula just because when astronomers first were looking at these, they thought that these objects appeared to look like planets, but they are indeed white dwarf stars with gaseous nebulas expanding away from them. Here's a very interesting picture with a lot of bright objects. One might first erroneously conclude that this is a bunch of stars, but actually this is the Hubble Space Telescope looking as far as it can into a vacant part of the sky so that it can see pretty much to the depths of the sky. And in this sky are a lot of bright objects, most of which, 99% of which, are indeed galaxies. And galaxies hold hundreds of millions, possibly billions, of stars in themselves. So each of these bright objects of different shapes and different kind and different orientation to us are indeed galaxies holding hundreds of millions of stars themselves. Gives you an idea of how vast the universe is and how small we are indeed in comparison. Here's Galileo Galilei, often regarded as the first modern scientist and the father of the scientific method, which has helped progress the science and technology in the last 300 or 400 years. In this course, we are going to use the System International unit system, otherwise called the metric system. There are three System International units we will consider in particular: the second, the meter, and the kilogram. The second measures time, the meter measures distance, and the kilogram measures mass. In the metric system, it is based on powers of 10, and here are some prefixes of the metric system. We have nano, which is 10 to the minus 9, that would be 1 billionth of something. Micro, 10 to the minus 6, which is 1 millionth of something. Milli, 10 to the minus 3, which is 1,000th of something. Centi, 1/100th. Deci, 1/10th. Kilo or kilo, either one is correct, is 1,000 of something. Mega is 1 million of something. Giga is 1 billion of something. A lot of these prefixes we might be familiar with from computer technology when dealing with megahertz or gigabits, gigabytes. Nanotechnology is looking at things on the size of molecules or atoms and trying to build things on that scale. A tera would be the next on this list, 10 to the 12. That would be 1 trillion of something, 10 to the 12. 10 to the 12 would be a million millions. So in other words, if you were to spend, say, $1 trillion, that would be the same as if you were to give 1 million people each $1 million. So a tera, a trillion, is a very large number. The first major unit that we use in the System International was the second. It is measuring time. What do we think of when we think of time? We consider time as being the continuous forward flowing of events. So where did the second come about? Possibly the second was originally a heartbeat, because if you think of it on the average, a heartbeat would be about 60 or 70 beats a minute, and that's close to a second. It's really hard to know exactly where the second came from, but that's probably a good guess. That's not accurate enough for most science, so in 1900, the second was defined as 1/86,400th of a mean solar day. For the life of me, I don't know why they didn't choose a nice solar day as opposed to a mean solar day, but that's what they did. There are approximately pi times 10 to the 7 seconds per year. In other words, if you were to calculate 365.25 days, 24 hours per day, 60 minutes per hour, and 60 increments of a minute, you would get 3.16 times 10 to the 7 seconds. So as a rule of thumb, you can just remember, if you wish, that there are pi times 10 to the 7 seconds in a year. Length. We measure length in the metric system by the meter. In 1799 AD, the distance from the North Pole to the equator was defined to be 10 million meters. So basically, by definition, in 1799, that would set the circumference of the Earth to be 40 million meters. Because if you went 10 million meters from the North Pole to the equator, and then went from the equator to the South Pole, that would be another 10 million meters. From the South Pole back to the equator, 10 million meters. And from the equator back to the North Pole, 10 million meters, giving you a total of 40 million meters for the circumference of the Earth. And that would be going from pole to pole around that way. But if you went around the equator, you would have yourself another great circle, and that circumference would be approximately 40 million meters. The Earth is not a perfect sphere, so it kind of bulges at the equator, so that's not exactly 40 million meters by definition, but it's pretty close, and within three significant figures, 40 million meters by definition. That's not good enough for most current science, so currently the meter is defined as the distance light travels in 1,299,792,458 of a second. This is kind of beautiful in a way, because the first measurement we defined was a second, and now we're defining the length measurement in terms of a universal constant, the speed of light, and the first unit that we defined, the second. So the meter is a fraction of how far light travels in a fraction of a second. So that's kind of neat. Here's some more lengths. The astronomical unit is the distance of the Earth to the Sun. That's 93 million miles, or 150 million kilometers. The first Who Wants to Be a Millionaire $1 million question was, what is the distance from the Earth to the Sun? And your possible answers were 93 million miles, 9.3 million miles, 930 million miles. I believe the person who answered that question had to use their lifeline. They had to call somebody. I wish they would have called me. They could have called any physicist or astronomer, and they did get the question right. So knowing astronomy and knowing these kinds of things possibly could win you $1 million someday. We're interested in even larger lengths than the astronomical unit. The light year is a much longer length. It is the distance light travels in a year. Light travels at 186,000 miles per second. And so if you took those pi times 10 to the 7 seconds of a year, then you would get how far light travels in a year, which would be 6 trillion miles. We already know how big a trillion is, or about 10 trillion kilometers. The parsec is even a larger distance. It is 3.25 light years, about 3.25 light years. We're also interested in mass. Mass can be measured or defined as a gram. A gram is 1 cubic centimeter of pure water at 4 degrees centigrade. Why 4 degrees centigrade? Because that's where water in a liquid form is at its maximum density. Water is very unique in that it gets more dense as you cool it down from room temperature, but when you get to 4 degrees centigrade, it reaches its maximum density, and then from that point on, as you continue to cool it, it starts becoming less dense because it's a polar molecule, and it starts forming a nice structure for its solid state. So when it actually forms ice, it's actually less dense than the liquid water around it, and hence water in its solid form will float upon its own liquid. That's a good thing because as water freezes then, it will freeze on the top of bodies of water like lakes and oceans rather than freeze on the bottom, which would kill a lot of the life as we know it on the bottom of oceans. Hence, for life as we know it, it is a critical thing that water has this property. Most liquids do not have this unique property. The unit used in the System International Unit System is actually the kilogram, which is 1,000 grams. Is the only SI unit that has a prefix in front. What is beautiful about this definition of the gram and the kilogram is the fact that we use a previous definition, the meter, and in fact a fraction of the meter, the centimeter, and say a cubic centimeter is a gram of mass. A cubic centimeter of water is a gram of mass. So we take a previous unit and define the new unit of mass in terms of water, and water is a good substance to use because we are 95% water, and everywhere we want to be in the universe, water better be there because we are 95%. We're going to need it. And so if we want a standard of mass, then water is a good thing to have. 1 liter of pure water is 1 kilogram, and the weight of 1 kilogram on the earth is 2.2 pounds. So if you have yourself a liter of water, which would be more than this, but if you have yourself a liter of water, that is 1 kilogram of water, 2.2 pounds on the earth. The standard kilogram is located in France. It's encased in a bell jar, which allows it to be in a vacuum so that would minimize the atmospheric. A kilogram is made out of platinum iridium, and so that doesn't oxidize too easily to begin with. And as they enclose it in a bell jar in a vacuum, that would reduce the oxidation on this standard kilogram over time. And they even have an extra bell jar, a double bell jar, to ensure that it's purely in a vacuum. So you have a vacuum within a vacuum. But even with all that precaution, the standard mass does change in mass over time. So we will probably see a more standard mass established in the next couple of years as scientists get together and decide on a standard mass that will not change from year to year. Okay, take a look at this image here. It's a parallelogram, and we have 2 lines, 2 blue lines, A and B. And I tell you, to my observation, as I look at this figure, it certainly looks to me that length B is longer than length A. It's just a matter of my perspective. I know, and you probably have some intuition on this as well, that in reality, A and B are the same length. So it's an optical illusion. But I would swear, to my best of my ability, that B is longer than A, and to be honest, I would be wrong. Take a look at this image. A bunch of squares there, black and white squares, and there's some lines. And looking at this image, I would say those lines do not look parallel to me. But in fact, in reality, they are. And if I were to measure these lines, actually conduct an experiment and measured the distance between the lines all the way along their length, then by measurement I could prove that they were indeed parallel all the way along their length. The point is that visually, I would immediately conclude that they were not parallel. They don't look parallel to me. I'm being fooled by an optical illusion. Scientifically, I could go in there, make the measurements, and conclude conclusively that they are indeed parallel. What does this tell you? It tells you that my eyes can be deceived, my initial conclusions can be deceived, but the scientific data that I can collect on this cannot be deceived. It would be absolute. Take a look at this image. Not too long, because it might give you a headache. But looking at this image, it appears to me, at least to my visual eye, that these dots are rotating. One is rotating one direction, the middle one's rotating clockwise towards me, and so forth. But if you were to focus just on one dot, one blue dot, you would see that it actually was not moving. In your peripheral, things are moving, but as you focus on any particular point in this image, you would find that that point is indeed not moving. So what's happening here is the physical structure of my eyes and my brain, the way that information is collected on your retina with all the cilia, and the way that that's transmitted through the brain, and the way that the brain tries to figure out what's before you as far as images, is fooling you into thinking that something else is going on here, when in reality nothing's moving. Here's another similar idea. As I look at this, it appears to me that some of these circles are moving, rotating, they're moving in different directions. But if you were to focus in particular on one circle, you wouldn't recognize that it was indeed not moving. Any particular circle you focus in on is not moving, and in your peripheral, everything else seems to be moving. Again, it's just a matter of the physical nature of the eye and of the brain that is fooling you into thinking something else is happening here. Again, all the lines on this picture are parallel, either vertical or horizontal, but it appears to me like there is some kind of sphere coming out of the page, and that appearance is just an optical illusion. Here's a checkerboard square with a figure, and we have a shadow on this figure, and the question is, which is darker, square A or square B? Looking at this figure, to my brain, to my eyes, it definitely appears to me that square A is darker than square B. And if I could conclude that, I could bet the house on it and say, definitely, A is darker than B. And maybe I'd be so sure of it that I would write a paper on it and say, by golly, A is darker than B. I stake my reputation on it. I stake the house on it. I publish that, and what might be true, the reality is, scientifically, that I would be wrong. Because here, as we compare, if you look in particular at this square, which is the same color as A and B, and you focus in on A, you see that A is the same color as this rectangle. And you focus in on B, and B is the same color as this rectangle as well. So they actually are indeed the same shade, the same color. What's happening here is that your brain is expecting that things in shadow are going to have the effect of the shadow on them, and hence, if they appear lighter in the shadow, they must be lighter than something that appears to be in the light. And it's just an effect of the brain playing the trick on you. So what is my point with all this? My point is that we can see things and we can conclude things based on particular observations from our eyes and our brain, but that does not establish absolute truth. The truth is when you actually conduct an investigation scientifically, collect data that can be analyzed and critiqued, and you come up with some definite result based on that data. In other words, in order to establish a scientific truth, it's not based on my opinion or my belief in something. It is based on scientific data that can be collected and analyzed and critiqued in a universal way. In other words, we have to conduct the scientific method. In the scientific method, observations are made. If there seems to be some regularity to the observations, then a hypothesis for the observations is made. A hypothesis is a very tentative explanation of some regularity or relationship in nature. I might come up with a hypothesis for what I observe. To test that, I will conduct a controlled experiment to test the validity of my hypothesis. I'll come up with some results of that experiment. When I'm done with that experiment, I either can confirm my hypothesis or not confirm the hypothesis. I conduct the experiment, and if I feel that my hypothesis is correct, I publish this. I don't go to the newspapers, I don't go to CNN, I don't go to Fox News, I don't report this to the news. I publish this and let it be seen by the rest of the world, and in particular by peers in this field who can critique my whole experiment, and in fact try to repeat my whole experiment exactly as I've described it. So this can be repeated on the other side of the world, and they will do everything that I said that I did, and if they see the same thing, then they will write, "We have concluded that we see the same thing as a result of this experiment," and everybody around the world will conduct this experiment, and if everybody agrees that my hypothesis was correct and the results fit by experiment, then we establish a small scientific fact. And now the way of knowledge is established by one little step of a scientific fact, and now we can go on to building further on that. But as we see, this is really hard to take that first step, because you can make observations that are totally wrong, and once you've conducted this experiment, they will bear to be totally wrong. So in other words, if somebody can find something wrong with your experiment, they will, and they'll publish that because they'll get credit for that. So to establish that we have a scientific fact, it definitely has to be correct scientifically. Once you have an accepted hypothesis, you may come up with a theory. A theory is a well-tested explanation that seems to work for what you observe. If any observation disproves a theory, then the theory must be discarded, or it must be modified to include this particular observation. In other words, there is no theory that exists that is already proven wrong. Because if it's already proven wrong, you throw it out. Or you have to modify it, which nobody really likes to modify theories too much, because then it gets too big. But you have to either throw it out or modify it to include all the observations made. So, a theory in science is far more strength-wise, far more validity to it than, say, a theory in a courtroom. You know, if you're in a courtroom, maybe you have a theory of who committed the murder. Maybe Professor Plum committed the murder with the dagger in the kitchen. And that's your theory, and it may be supported by circumstantial evidence and maybe an observer and that sort of thing, but you could be wrong. There's a lot of ways that you could be wrong with that particular theory. A lot of it has to do with your subjective opinion. But in science, a theory that has survived has been scrutinized at every possible point, and if it's still surviving, it is pretty strong. At some point it could be proven wrong, but a lot of times trying to prove it wrong will just collect more and more data and if it survives from that scrutiny, then it's actually getting stronger. A fundamental regularity or relationship detected in nature can sometimes be called a law. So if you had a theory that seems to never have any exception, and actually all the billions of observations made by billions of people over millions of years have never proven to have any observation that proves it wrong, then you might call that a law. The reason I went through this discussion of the scientific method of theories and laws is because we have to use science and scientific methods to discern things in astronomy. In astronomy, we've never been to these places that we're going to talk about. Most of the places. We've been to the moon, but beyond that, we've sent some probes to the outer regions of our solar system. But most of the things we get from astronomy are from data that is coming to us in the form of light. And so to understand what we discern from that data, we have to understand the nature of light. And so we have to break light down into its different aspects, its wave aspects and its particle aspects, to understand how we know how far away something is, how we know how luminous it is, how we know how old something is, how do we know how much matter is there, how do we know what it's made of. All these things we get from light. All this information is coming to us from light. And so we have to understand the nature of light, the theory of light, and hence the basis of astronomy. So we have to believe in the scientific method. Okay, moving on to some definitions that we need to familiarize ourselves with here in the prologue. Here we have the Earth. We have the North Pole and the South Pole, and we divided this Earth up into lines that happen to be parallel to each other. We call these lines parallels, or lines of latitude. The longest line of latitude, the longest parallel, is the equator, which happens to be a great circle. A great circle is a line that has at its center the center of the Earth. So the equator is a great circle that indeed has its center of that line, which goes all the way around the circumference of the Earth, the center of the Earth itself. The equator is the only line of latitude, the only parallel, that is indeed a great circle. This latitude is measured in degrees, 0 to 9 degrees, north or south of this equator, equator being 0. So if we go north of this, we go to a positive latitude of 9 degrees up to the North Pole. If we go south of this, we can go to a latitude of 9 degrees south, which would be negative 9 degrees in terms of latitude. As stated, the equator is the longest line of latitude. All other lines of latitude will be somewhat shorter than that as they go around the Earth. Here is a monument built on the equator. It's in Ecuador, and this fellow is standing near this monument, so it designates where the equator is going through. And in fact, There's the equator. So he seems to be just a little bit south of the equator. Here's the Earth, again divided into lines. These lines are extending from the North Pole to the South Pole and then back again. These are lines of longitude. They are not parallel. They converge at the poles. So they converge at the North Pole and the South Pole. We define the zero line of longitude as a line that goes through Greenwich, England, because that was the center of the world, or the center of commerce, at the time that this was established. So we go through Greenwich, England, for 0 degrees longitude. Longitude is measured in degrees, 0 to 180 degrees, east or west of this Greenwich prime meridian. If we go east, eventually 180 degrees will put us on the other side of the world, and that line at 180 degrees east, or equally well 180 degrees west, is the international date line. So international date line is exactly opposite the prime meridian. The international date line would not necessarily be a nice straight line of longitude because it has local variations to take into account time zones for localities there, but it is on the opposite side of the Earth. Here's a line of longitude from the North Pole to the South Pole and back again. If we just consider half of this line, that is called a meridian. So the line that goes from the North Pole to the South Pole, a line across the surface of the Earth, is a meridian. With these lines of longitude and latitude, we can break up the surface of the Earth, which is a two-dimensional surface, the surface of the Earth itself. We can break it up with these two coordinates, latitude and longitude, and hence create a grid that will help us locate, in particular, any point on the surface of the Earth. Lines of longitude might be divided. You're going to divide 360 degrees all the way around the Earth, and the Earth turns on its axis in 24 hours. So if we associate 360 degrees divided by 24 hours, or 15 degrees per hour, we can create ourselves a grid in longitude that would also correspond to time. So every 15 degrees of longitude corresponds to a time zone on the Earth, of each zone being 1 hour. But again, we want to allow for local variations, so the lines of longitude that extend every 15 degrees will have, at least for time zones, local variations that allow commerce to be conducted at its maximum efficiency. So here in the United States, we would have the Eastern time zone, which is more or less centered around 75 degrees west from the Greenwich prime meridian. The Central time zone, which is at 9 degrees west. The Mountain time zone, 105 degrees west. And the Pacific time zone, 120 degrees west. If we look in particular at the Central time zone, which we're in Alabama here, we see that it has been extended to include us and parts of Florida here. Indiana probably should be in this time zone as well, but it is not. So it's indeed in the Eastern time zone. So we have this local variation that's included Alabama in the Central time zone. This two-dimensional surface of the surface of the Earth needs only two coordinates to establish a point, and in particular, Those coordinates are latitude and longitude. If we go 77 degrees west from the Greenwich prime meridian, that would establish a meridian, a line, from the North Pole to the South Pole. Now, if we go 39 degrees up from the plane of the equator, from the center of the Earth, that plane of the equator, up 39 degrees, would establish a point on that meridian line, which in this case would be Washington, D.C. So Washington, D.C. would be located at 39 degrees north, latitude, 77 degrees west, longitude. So latitude can be thought of as degrees north or south of the Earth's equator. Longitude can be thought of as degrees east or west of the Greenwich or prime meridian. If we were able to cut along these lines of longitude with a very, very sharp scissors, we could cut along these lines of this two-dimensional map that is on this sphere, and then we're going to pull this map out so we can make it flat. And what we would get would be something that looks like, not gingerbread man. If we pulled it out, we would get something that looks like this, which would be a flat map of this spherical surface. As we see here, though, where we've cut it, this flat map of this spherical surface would be more or less pretty accurate if we're near the equator, because there's not too many cuts near there. But as we get away from the equator, either to the north or to the south, we find that there are large gaps there, and hence we would have a lot of discrepancy as far as trying to build a two-dimensional flat map for a spherical surface as we get away from the center of that map. So we fill in those areas, we would get a map of the world that is a flat map, a Mercator projection of the world. And again, near the equator, it's relatively accurate. As we get towards the poles, it is very distorted. Hence, Russia looks very distorted. So does northern Canada. And Greenland, which is a big island, but it's nowhere as big as depicted on this map, is a very large island, very distorted. Antarctica, which is at the south of this map, looks huge as it extends across this whole Mercator projection. But in reality, Australia is about the size of, Antarctica is about the size of Australia. So Antarctica is very distorted on this map. If we use longitude and latitude on this map, we can create a grid where we can locate different places on this map. In particular, if we were to locate, say, a place like Washington, D.C., we can locate with latitude and longitude as a point on this two-dimensional map. 39 degrees north latitude, 77 degrees west longitude. And we can even go down to more minute points on this map if we divide our degrees into minutes and divide our minutes into seconds. Note that on this two-dimensional map, longitude, which is really not parallel, now appears to be parallel on this two-dimensional map. Here's a map of Alabama. We look at the outline of it. And we see as we look at Alabama, we are actually located between 30 degrees north to the south and 35 degrees north to the north. In other words, the border of Alabama with Tennessee is the 35 degree north parallel, or 35 degrees north latitude. And below Mobile here is the parallel of 30 degrees north. So the whole state of Alabama is located within 5 degrees of latitude. And 3.5 degrees of longitude, because 85 degrees to the west, or 85 degrees west, will define at least part of the eastern border of Alabama, and 88.5 degrees west would be the western border of Alabama. 88 degrees 30 minutes would be 88.5 degrees. As we look even more closely, focus in on where we live. Here's northern Alabama. And in particular, if we look at Scottsboro, Scottsboro is at 34 degrees, 39 minutes north, 86 degrees, 1 minute west. So that would locate the city of Scottsboro. Huntsville is 34 degrees, 42 minutes north, 86 degrees, 35 minutes west. And Decatur is 34 degrees, 37 minutes north, 86 degrees, 59 minutes west. We can see for the most part that these three cities, Decatur, Huntsville, and Scottsboro, are pretty much on the same level, pretty close to being at the same latitude, within a few minutes of each other. But there's about a degree of longitude that separates Decatur and Scottsboro. Now, the sun, or the Earth, rotates 360 degrees in 24 hours, 15 degrees per hour, which is 1 degree per minute. So, the Earth would rotate 1 degree per 4 minutes, sorry. The Earth would rotate at 1 degree in 4 minutes. So if you were in Scottsboro and you observed exact noontime with the sun overhead on your overhead meridian, then 4 minutes later, Decatur would observe the same thing with the sun on their overhead meridian. So the movement of the sun from noon in Scottsboro to noon in Decatur is 4 minutes. That concludes our first lecture on the prologue of astronomy.